Hi, everybody. Thanks for showing up in numbers, still in numbers. 6 in the evening, a bit of a difficult time for some. I appreciate it. It is a good time for industry lecturers. Maybe it'll work for you as well. So it's always good to appear in class. Thanks for those coming in class. Thanks for those coming in Zoom. Thanks for those watching on YouTube. Anyway, welcome to the second day, third hour. There was already some troubleshooting happening here. A peer helped another student solve the fact that notebook in iJulia was spawning onto VS Code because VS Code in the Windows was the default HTML viewer. So that's a spirit. Please try to do that as well if you can via Ed. You know this in other courses, but in the computing stuff, it really even more. One thing I didn't say yesterday we're still actually waiting to get the tutor hours for Ed. So how much time our tutors will be able to spend on Ed. But no matter what it is, our policy is always kind of a 24-hour delay with staff answering. So you can post a question on Ed, peers can answer instantaneously, staff answer with a 24-hour delay. Okay, and in the 3 days prior to submission, you might have noticed in the course kind of schedule, when we have a submission on Friday, 4 in the afternoon, then there are no practicals. So it's kind of from Wednesday, you're on by yourself, but with peer help in Ed. So the staff also won't help with Ed on the 3 days prior to submission. Okay, just to be clear about that's because then, so you know ahead of time. So it's kind of no last minute fixes. It just seems to work a bit better this way. So there's not kind of cramming, hey, last second, how do I do this? Are there questions about the schedule or the course or anything else before we continue cracking? No, everybody's happy? Sort of, good, okay. Just so we see where we are. So we're now going through this, what we call the boot camp, but frankly, we were all over the place. We'll try to focus today and get to some basics of programming, just so we come out of this hour with the paradigms, and we'll still have another hour of that on Monday. But then in the second hour, you'll have the excellent perspective seminar of Dr. Megan Dawson. So please, those at home also try to come in person for that seminar. And then on Tuesday, we'll have a practice quiz. So practice quiz doesn't just mean that, and ideally come and do it in class, but if you can't, you can also do it in home. The actual quiz is not like that. The actual quiz, you'll need to come to class unless there's some special consideration or something like that. Practice quiz, you could also do at home, but of course, please come to class and do it. The idea is that we'll do a quiz and then we'll also discuss the solution. Okay, so there'll be some learning in that Tuesday, in the practice quiz. Okay, so our goal with Unit 1, which we called the Hello World Bootcamp, was to basically get going with some basic programming. But since there were so many hands up of people that actually did Python in one way or another, I did get a bit deeper and show some Julia things here and there that are beyond the basic programming. But then back to the basics, what our goal is to kind of understand these constructs, perhaps, which are maybe the kind of the main things that make up this programming language that we're going to deal with. Now, if you're into computer science and into a lot of details, a programming language can be imperative and declarative and can be functional, procedural, object-oriented. There are all these ways of describing what a computer programming language is, but in a sense, you often need to have some of these constructs. Some languages have more, some languages have less, but these are quite standard things. You'll find them in almost any programming language. Okay, so we saw what variables are, right? We understood what that is. And we saw that variables also have a type, right? The variable can be a string or it can be an integer, int. What did we call that type? Int 64, right? There happens to also be in Julia an int 32 and an int 16 and an int 8, I believe. So there are many types, okay? And you'll deal more with that. But you can have floating point numbers and you can have other types as well. We've used built-in functions. We haven't done this macros. We haven't used a macro. So a macro is kind of like a function, but let's just see it in action. So if I now, yeah, maybe this is, yeah, like this. So let's do x equals 7. So here's my variable x. I'll just put a semicolon to suppress the output, right? Now I can, of course, do println of x. What am I going to see? Am I going to see x? Am I going to be set, or am I going to see 7, or will I see both? What will I see? 7, right? So the println function, in fact, when it's implemented, when it runs, it doesn't even know that what I'm giving it is x. It just knows I'm giving it 7, right? Like, look, if I do println 7, I'll obviously also see 7, right? This wasn't 7 the string, this was 7 the integer, right? But the println function in both of these cases felt the same, had the same experience. The same bits were flowing through the CPU, okay? The same order of execution. It got a value that was, in one time it was x, another time it was 7. Just like, what's something else I can put to help the println function have the same experience, the exact same experience? 3 plus 4, perfect. Okay, right? Also, println doesn't know that it's getting 3 plus 4. 3 plus 4 is evaluated, and then println gets it up, and it got a 7, right? Okay. Let's do something else. Let's do @show. Now, this in Julia is the way to invoke a macro, okay? Just like I'm calling a function, I'm invoking a macro. A macro is kind of like a function, but it does something a bit more. So I'll do now @show x. Okay. So what it does is it actually says that value x is 7. The macro was actually computed at some higher level before the programming language actually went. And there's a whole bunch of the processes that happen, and the other lecturers will speak about it. Julia converts to lower code, and then converts it something to LLVM, which is low level virtual machine code. And then that's compiled to machine language, and all this is happening, right? But the point is that this macro was aware that this is an X, right? And if I do show 7, it's aware that what I'm giving it is 7. And if I'm giving it 3 plus 4, it's aware that that's what's happening. Okay, so that's a macro. First of all, when you see that is macro, and actually macros can be even called without those brackets. So both ways of using the syntax are okay. So this one is equivalent to this one. Now this is actually useful for debugging, right? So when you're actually running a program and you have a variable inside and you're not sure, I mean, here we all knew x was 7, okay, but we're not sure what x is, then we put that @show line in the code, and it actually prints it to the screen, and it doesn't just print 7, it prints x equals 7, right? Now, also when you're doing scripting, if you're doing more, so, okay, like this, I have pause for a second. So if I'm using now, let's say this program, or maybe it's my mail program, or maybe something else, do I know how the programmer called the variables? No, typically no, right? So, I mean, unless it's somehow exposed to me in some obscure error message, I typically don't know. We don't know how the programmer, if they named it X or Y or X underscore total budget for the day or whatever, right? But when you're doing something like this, you're actually exposing that variable to the person seeing the output, right? Now, when you're actually doing scripting, that's okay. That's pretty useful, okay? Because scripting, I mean, you're using the programming language for scientific purposes. You're doing some analysis. It's pretty useful to use this show, okay? So that's the smallest thing. That's the most basic thing we have about a macro, but you'll see them more. All right. So that was this type of stuff. And now let's get to kind of the beans of computer programming and logic, and let's do some logical statements. So scroll down and we see what we had here, a suggestion. So first of all, there are just two values which we can have, true or false, okay? So true is just true. Type of true is a Boolean, okay? A Boolean, 0 or 1, all right? And the opposite of true is false, okay? How do you do it in Python? Exactly the same. Capital, right? There's small syntax difference for Python, capital T, capital F. Okay. All right. So things can be true or false. It's important that things can be true or false. Then we can have all kinds of logical statements. So we can ask, does 5 equal 3 plus 2? I wrote does 5 equal, but what did I put here? Equal equals. Okay. So this is kind of the biggest thing that some people, maybe if you've never programmed, you've never seen something, you go to equal, there's equals, equals. Equals actually has different meanings. So this equals equals is the equals we know in mathematics, right? Whatever's on the left-hand side equals the right-hand side. Okay, only now here we're actually checking if that's correct. All right. Whereas this equal that we had, what was this equal? What would be a better name for this equal? Here, this one that we had here. Was this checking if x equals 7? What is it? Assignment. Assignment is what's happening here, right? So thank you. We're assigning the right-hand side to the left-hand side. In fact, in some programming languages, some of you have done R. Who's done R? A bit. Oh, stat 1301. Most of you have done, right? So in R, it's standard. You can use equals, but it's more standard to do assignment. Okay, that derived from my old language that was called S+, but it's actually a bit more natural, that arrow going left. A bit not as syntactically nice. Okay, so what's going to be the result? True. Okay, not so much a test of your mathematical abilities, but more of what's happening. Because I guess a harder question is what's going to be the result here? I would hope, right? So what are we trying to do? Assignment of 3 plus 2 going into 5. And invalid assignment location 5 around REPL 13.1. So REPL 13.1 relates to this place. That's not a great way to describe this error message, but we understand what's happening. Okay, so 5 here is something that we can't change. Okay, so now that we have this check of equality, of course, we can do checks of inequality. Does 5 not equal 3 plus 2? Not equal is not equal. What's going to be the result? True or false? False. Okay, because 5 does equal. Now, I didn't really have to do this because what I can do, well, I did. Let's say like this. If somebody wakes me up at night and says, "Hey, Yoni, okay, we have to cut the Julia language. We need to throw away some things. What do you want to throw away?" This not equal would be maybe. Well, first of all, say I would need it. Like foggy, don't know. But this would be one of the things we could throw away. Why can we throw it away? Because look, what's not of false? True. Okay, so not is negation. Do you do it in Python with a tilde or with a not? Or with an exclamation mark? Oh, not. Right, sorry. This is, it's, okay. Thank you. So in Python's more literal. You write not. Okay, and in some languages, you put a tilde before. Okay? Just like, and of course, there's this, when you did, maybe if somebody did math 1061, etc., there's this mathematical not, right? Okay, so how can I now emulate this statement with the not and with an equal equal? You just say not 5 equal 3 plus 2. Right. So that not equal just says it. Okay, I think you can. All right, so these are basic comparisons. Of course, I can do some comparisons like this. I can ask, is 5 greater than 5.1? It's false. Is 5, look at this one, I can do greater or equal than 5.0. What do you think is going to be the result? True. Now, am I comparing things of the same type, do you think, or not exactly? Well, so what's the type of this guy on the left? Integer, and the guy on the right? Float, right. So, and if you'd want to be specific, it's probably an int64 and a float 64, right? By the way, you can do float 32 and float 16. And in this course, you'll get into the structure, the bit representation of floating point numbers. So what's happening bit by bit, right? There's a mantissa and the exponent and the sign. So it's kind of nice that you do that if you have not. Okay, So this is still going to be true. I can compare two things that are numbers, even if they're not of the same type. I can even be like greater than equal tab 5.0, and then my programs look much cooler. So this is exactly the same. Okay. All right. So you can do logical statements like this. Yeah.
I saw just is usually these commands that you press that, are they usually similar to LaTeX?
No, they're exactly. They're exactly. They're exactly. Now, there is a way to actually see how to do it by highlighting, but I'm not sure. And that's why when I write the code examples, I typically, like if this was in the notes, then you would see like this, and I'd do GE plus tab. What is this hash, by the way? Comment. So I'd put a comment like that, all right? Yeah, so I forgot what's a bit, because actually it's kind of annoying. So if you get to the Julia documentation, people in Julia got way obscure. They're using characters that are out there. And sometimes you just don't know how to actually put the character in the keyboard. So your only way is to go to the documentation, select the character and paste it, right? So now these are actually Unicode characters, right? So each one is a Unicode. And you've got, by the way, I can do like X. Look, I can do X hat 2 tab. Look, X squared, right? So I can do X squared equals 9. This looks impressive. We feel that we are in the 22nd century where we got X squared. So if I put X, what will I get? No, we're still get a 7 because it's a different variable. Okay, so things can be, you're right. Things can be a bit daunting. That squared, that little superscript squared, is nothing but a Unicode character of the upper script squared. Okay, so X was 7 from before. Okay. Yeah. Yeah, the whole name, it's like, say I didn't have, I would call it X squared, right? So say often you do statistics, and often the variable you care about is sigma squared, right? So you might call your variable sigma squared, and you say, your sigma squared is 9, right? But of course, Julia, so I can maybe just give it a nicer name, sigma squared, and I call it 9, but don't expect there to be a sigma in the system. Sigma is not defined, okay? It's just syntactic kind of sugar. Okay, but still it kind of makes, there's a nice book, Algorithms for Optimization book. So if you look at this book, I think it's free online as well. It's all in Julia code. And the fact is, just because of this Unicode stuff, even though you can do it in Python, it's not as common. It's kind of become very ingrained in Julia. So Julia is kind of a bit more mathematical. So like this book, for example, which is, a book about optimization, everything is in Julia code, and it kind of looks not so far from the pseudo code. Okay, to not have to name the variables. Yeah. Mm-hmm. Exactly, just another character. But of course, sometimes it's a bit deceiving, because if I do, for example, square root tab, and I do square root of 121, this did apply the square root function. Okay, so in a few specific things, in square root, in pi, I don't have the complete list, but it'll be in the Julia documentation, which is quite readable, right? But then you see it kind of, and this kind of looks impressive. Okay, a bit. Oh, and 2 in 1, 2, 3. So we haven't seen this yet, but this is an array. Okay, an array. If you're in Python, what would you call this? A list, right? Right. So Python has lists, kind of the basic thing. Python also has 2 tuples. If you're doing NumPy in Python, if you're doing any sort of numerical mathematics, you're doing NumPy, then it's called NumPy array. In Julia, it's just arrays. We'll get to it. But this operation, 2 in, what is this going to be? Error, true or false? True. Okay. So this was just like doing the in function applied to 2, 1, 2, 3, or, sorry, close brackets, or doing 2 in 1, 2, 3. So it's again a logical check. Okay. But of course, one last thing, sorry, we're just, see, that's a prompt. We start doing, and then we digress. So what's this? Is this going to be true or false? False, but I see 2 in 1, 2, 3. Why is it false? The string 2, thank you. Right, okay, good. Right, so there's no string in the array 1, 2, 3. Okay, so we can do algorithms for optimization another day. And now we come to the most important kind of operations, logical and there's a typo here in the notes. This should be a logical or. Okay, so this comment here is a typo in the notes. Logical or. Okay, so true and 2 is less than 5. How is this going to evaluate? True. And false and 2 is less than 5? False. And this is a logical or. True, right? Because we need one of them to be true. Okay, good. So that's and or. Do you know what other languages have and or exactly like this? C, yeah, C, C++, right? C, that's the basic way. And there's a bit more, so we're not going to be exhaustive in all the operators, but these are the kind of the basic logical operators. So, well, why do we want to do logical operators? So let's make a variable I am happy, and let's call that variable true. Okay, so variables can also be Boolean value, right? Boolean value. And let's say if I am happy, println party time. What do I need to have it at the end based on what you know in Julia syntax, kind of? End, right? Not nice like Python where you don't need to have the end, but nice like, well, and not nice like Python in the sense that also would have forgiven for my formatting to be bad, but this is a nice way. What are we going to get? Well, party time, right? But if I'm happy was false, now instead of doing false, let's do that pi is greater or equal, or let's do less than or equal than 3. Okay, just something a bit more complex. So what's happening here? Well, we have to kind of rely on the way Julia is wired, and the order of operations is that this is evaluated first. Okay, right? That's kind of important. Otherwise, this will make sense. All right, so you can always put these brackets. Okay, so this is pi less than or equal than 3? False. I'm happy will be false. Okay, and this would have worked if I would have not had these brackets, just because the assignment operator here of this Boolean happens after this thing happens. And now, are we going to get party time? Sorry, no. Okay, no party time. Okay, so conditional statements. In the computer, often in like in the minimal language, in assembly and whatever the CPU runs, often what you need is just a conditional statement and also something called like a goto, like a jump, right? With that, you can do everything. You can do loops, you can do everything else, right? If you had that, you can do everything. Some CPUs have more under the hood, some less. You'll hear about more of that from the other lectures. But we don't have gotos, but hence we have functions to do things to go around, etc. All I'm saying is that the conditional statement is very strong, and we can do quite a lot of things with it. Okay, here's some bit of code. Okay, so using random. Now look, actually, hold on. So if I just do rand like this, I get a random number. I mean, random, you'll have a whole unit, pseudo random number. It's not really random. This wasn't kind of like looking at, you know, how many particles are in the atmosphere and then giving some random. I mean, there are real physical random number generators. This is random from an algorithm. What do you think is a range of random numbers that you get with the basic rand? What would you expect? 0 and 1. And the distribution is Gaussian? Normal? Uniform. Yes, okay, you guys are not taking any intimidation. Uniform. Okay, good. So uniform distribution 0, 1, that's what you would expect. Okay, and I run this again, I get a different one, and different one, and different one, a different one, a different one, and it's great, right? Now, Sometimes I want to actually set this sequence of random numbers to be deterministic in the sense that even though it appears random, it's going to be the same way every time I rerun my program. That's useful when you're debugging, and you'll have programs in this course where you do in the second project, right? And even though you get random numbers for what's happening, if you actually make it the same sequence of things that appear random, then if you have some bug, you can actually catch the bug in the same sequence. It can be good for that. It can also be good for simulation purposes. It can be good for, there's quite a lot of theory of why you would want to fix the something of random numbers. What do you call that something, if somebody knows? The seed, right? But some people have not heard what a seed is, right? So a seed is like the first random number. It's not really the first random number. Underlying the sequence, there's a sequence of some bits. It's the first set of bits that then kind of, from that, you get the random number. But let's set the seed. So to set the seed, what we need to do is we actually need, so random was kind of available to us already. Well, some things are not available to us already. Let's do using of the random package. You've done using for a different package already for iJulia, right? So I do it using random. That just takes all of the functionality, mostly functions, but also types, and perhaps some global variables available with a random package and puts it now in the namespace so we can actually call them. All right, as you do with other languages. You do library in R, import in Python, etc. Okay. Now, let's just say, hey, did I install the random package? I'll use a right square bracket, go to the package manager, okay, and do status. What packages do I have installed? I have HTTP, iJulia, JSON, primes, progress meter, and special functions, okay? I don't have the random installed. So why would I be able to do using random? Yeah, it's default library. Great. So thank you. There are a few default libraries that come with Julia. They include linear algebra. They include statistics, and a few more, maybe dates. But those are, like for us math geeks, linear algebra, statistics, and random, and we're pretty happy, right? These are the default ones. But then you got some. So okay, now they're all in namespace. We don't care. There was a big debate in Julia back kind of when it was formed about a decade ago. Do people need to do using linear algebra, yes or no? Because Julia actually tried to take the MATLAB space, and that's why some of the syntax is MATLAB-y, right? And in MATLAB, you got matrices out of the box, right? In Julia, you actually need to do now using linear algebra if you want to compute the eigenvalues of a matrix or something like that, right? Actually, Andy Ferris was lecturing here for 3 years, and this year he's taken a year off, and Claire is taken over on that role. He contributed to that whole debate, and also how matrices are organized and stuff like that. Okay, with all that digression, if I now do just random dot seed exclamation mark, and I'll put here some numbers. So let's put just some number. Okay, I'm going to call so all this was digression, digression, right? Using random dot seed. Okay, so I'm going to call the seed. Is it called the seed function or the seed exclamation mark function? The seed exclamation mark function, right? The exclamation mark is part of the function name. Why did they decide to put an exclamation mark? We said that kind of roughly yesterday.
Like changing something about random.
Right. It's changing something in the state of my system. It's actually changing the seed. It's telling, hey, random numbers, you are going to start with 1984. Okay, but there's also something else. You see here that actually I'm calling the module random, and in it, this dot has several uses in Julia. This is a dot you've surely seen if you've used Python. This is dot within random. Okay, right, so that's what this dot means. Okay, and it returned to me something that I don't really care about. I could have, of course, done this semicolon, and I would do the same thing. Now, I would have liked to actually do seed exclamation mark 1984. But then it tells me seed exclamation mark is not defined. So even though I am using the random package does not export the seed exclamation mark. It didn't want to kind of dirty my namespace. the whole concept, if you're hearing me, dirty namespace, right? When you're writing a program and then you have many variables, somehow names clash. You don't want all of the names in the world. Okay, and see the exclamation mark. I mean, so I'm not going to come home to my wife tonight and say, "Hey, see the exclamation mark." I'd probably survive the evening without saying this, right? But it's a bit of a common word, and that's why they didn't do that. Okay, so random see the exclamation mark. So now if I do rand, what number am I going to get? Is it 1984? No, but it's going to be a number that's reproducible. Okay, so let's just see this. Let's do rand and rand and rand. And now let's do seed 1984. And now what's going to be the first two digits of the number? Yeah. Okay. So, right, the sequence is reproducible. It always gets me. It's crazy. And you can run this for a trillion. You can run it for a whole, and it's all going to be reproducible. Computers are kind of deterministic. I mean, I think there is enough operations for you to run, and then one flip-flop in the computer will somehow change, but that's very unlikely. So it's a deterministic machine. Okay, so that's this. Why did we see all this? Just because this example has this, and this example has a bit more. So here, if the rand, remember I showed you that functions in Julia are kind of, they can do a lot of things, right? So the rand function, there's not just one way I can run rand. If I do methods of rand, I can run like 81 ways to run rand. Right? So there's 81 ways that rand operates. One way is if I give it this thing, I do like rand 1 to 10, and this thing is called a range in Julia, a unit range 1 to 10. Okay, you can think of it as like an array of a list from 1 to 10, but it's not really the numbers. It's like a specification of 1 to 10. Okay, do rand 1 to 10, and it's going to give me numbers from the range 1 to 10 inclusive. Right? At some point, I'll get a 10 as well. Okay, so I guess if we do X rand 1 to 10 and Y rand 1 to 10, by the way, some spaces are not needed. This space is not needed, but it's become kind of a bit of a programming style. So when you program, try to have some consistency in your white space, even in, I mean, things that are kind of no-go, no way to violate them are tabs and ifs and while loops, etc. Right? But stuff like this is also kind of nice to be nice. And you can, of course, use your editor as you become more hackery during the semester to help you do that for you automatically. Okay. All right. So what are we doing with this example? XY. Oh, yeah. Show XY. Now here, by the way, when I do this comma, what this does is it creates a tuple, actually. All right. Even though I didn't put brackets, it has nothing to do with the show. So look, if I do X, Y, hello, and pi, this is a tuple X, Y, hello, and pi, right? I actually didn't need the round brackets, and it kind of created, it's as though I had the round brackets around, right? So if I do show X, Y, then I just, and by the way, after the show, I could have put a semicolon, not to kind of have, because show also returned what we gave it as a return argument. That's why we saw it twice. Okay. So why do we do this? Well, we've got the random X and the Y, and I guess all we're doing is just this logical statement. Let's try and work out what it is. Always hard for me, because my brain's not so logical. Does X equals Y? Well, maybe it doesn't matter. Does it actually depend on what was? What do you call this in math? This kind of tautology. Yeah, that's a tautology, right? So no matter what the values of X and Y are, well, in this case, no matter what tautologies are not about numerical values, but are about the Boolean values that end up here, right? But we know here that this was like B and not B. Sorry, B or not B is a tautology. It's always true. So we didn't even have to have the random seed here. The only reason for having the random seed is that if you ever run this code, you'll get the same numbers here. Okay, so I think that's enough on logical statements. More thoughts? Logical statements? Okay, so then you can do the if, not if, you know, the world has gone crazy if 2 is less than 3 and 2 is greater than 3. Yeah, because you can't have both. The world makes sense. Let's not run this because it's obvious. And here you see your first else. So when you have a statement like this, if something, do something else, do the other thing, you know that one of the two execution paths are going to happen, right? For sure. Like you look at this, you know that after you've run here, you've either printed this or that, and x is less than 30, so it is less than 30. Okay. That's it. So that's a syntax: if, do something else, do something else. All right. Now you can also have, and this is also in Python, it's elif, right? Something like that. So you can do x equals 25.3. Is x less than 20? Well, print it's less than 20. If that didn't happen, check the next condition, right? So then print that happens. I could have now had more else if I wanted, as many as I wanted. And finally, the else is like the default. Okay, so that's how you do that. And here, if we want, for example, the absolute value, if x is negative, then println negative x. Else, what is the else? How would you define the else? Like, is x, like here, if you were to put a comment on this else, as we'll do in a second. Greater than or equal to 0, right? So it's not, x is non-negative, right? It's 0 or greater than 0, then println x. Okay, just to, yeah.
If you can see house here, you have to have that house.
No, you don't have to have that. So you can just do if, do something, otherwise no.
Like if house here, and without the last house.
Oh, can you do else if without? Yeah, you can do without the last else. Let's see. If true. Okay, let's do if false. If false, okay, I'm going to be brave, right? I am an idiot, but I know it's false. It's not going to print this. Else, if true, println, I think I am not an idiot. And else if 2 is greater than 3, which is actually true, then println I love you. End. Okay. So false. Thank God this is not going to be printed. The next condition is checked. True. This is going to be printed. Is this condition ever going to be checked? No. Okay. Okay. I think I'm not an idiot. It's a good conclusion. Right. Thanks for the question. All right. That was on conditional statements. The real nice stuff is this, and we won't do that. So you can do x equals 2 equals 3, question mark. The world is crazy. Else the world makes sense. So this is called, does anybody know a name for this thing? You've programmed in C, the ternary operator. It's like in C, you know, C was like invented in 1972 or something like that. Okay, and you know, all the operators were binary, like not is binary, right? Unary, not is unary, and is binary. This is ternary. It has 3 things. It gets something here, a condition. If the condition is true, then it does or evaluates to this. Otherwise, it evaluates to this. Okay, what is it gonna do? What's going to be the evaluation of this expression? The world makes sense because it was false, so it went to the second one. Thanks. Okay, so you can do a lot of that. People in Julia, they also do this. They do sometimes 5 equals 7 and error, or let's just say bad stuff. Okay, so Julia has lazy evaluation like C. Okay, so basically, if this expression is true, then it goes and it evaluates the next expression, right? Because with and, it's enough, right? If this is false, why ever evaluate this, right? I mean, just to see, the reason you would do this, like in principle for performance, is you check, like, let's just write now if condition and do some heavy computation. condition, right? So let's say, I want to check some condition. We all work like that, right? We actually order our life. We do the first thing first, which if we know that both of these things have to happen for something else, whatever that something else, right? If that condition is not satisfied, we're not going to do this heavy computation condition, right? So the latter won't run. Okay, but if we now do 2 equals 3, and let's say exit, okay, exit kills Julia. Is Julia going to be killed now? Oh, thank God, no, right? Because the first condition was not satisfied. And you'll see this in code, and we've even put it in the quizzes before, just because it kind of makes for quick code, but it's actually hard to read, because you read this and it's basically, if 2 equals 3, then do the other thing. The other thing in this case, exit also, it should have been exit exclamation mark, like it really changes our life, right? I mean, exit is, oh, it's dead, finished, we have to restart, right? But anyway, so that appears a lot in Julia, not in other languages. People program like that, and we do too sometimes. Okay, we move on a bit. 640, oh my God. All right, for loop. So you've already seen this for loop, but let's do a version like this. For nothing in 1 to 5, print len hi. So this says, I do want to run this thing 5 times, but I don't care if I'm in number 1 or number 2 or number 3 or number 4 or number 5 when I'm running it. Okay, so of course I could have called this variable Jeremy, right? But why make it less unreadable? So I would just call, it could have been I, J, K, Jeremy, whatever. So I'll just do nothing, and that's just a variant of that. Okay. But you can also, as you can do in Python, you can also do loops on collections, on lists. So you can do for I in, sorry, it's effectively the same. Sorry, 1 to 3. This in is just the same. Println I. Okay, that's fine. All right. You can also do println, sorry, you can do for I in, this in is just like this in, but this in you feel much more sophisticated when you do it. You can do hello, pi, goodbye, and 7. Println, now I have I. Sorry, that n didn't need to be up there. Okay, so I was one of the values of this thing, which officially we didn't tell you what it is yet, but it's an array. Okay, it could have been a tuple as well. Okay, it's a collection. Good. All right, so and now let's now analyze this logic. So now let's take a second and analyze this logic. Now, please ignore this global total. Okay, so the fact we have this global total is because we're running it in Weave. But if we were going to run this, so let me actually just now open it. So total, there's a kind of a story about this where I don't want to get into it, but global variables are they live outside of the for loop. And then if you're in the for loop, you have to, if you're going to make a change to this total, you have to say it's global. It's a bit annoying, frankly. But if we are in Jupyter Notebook, we can do it without it. So let's go there. But it would have not weaved without, it would have not rendered without doing this line. So let's go to the logic of this thing. Okay, so I'll delete this line. Total 0. Max val 10. How many iterations are we going to have? 10. Okay, in each iteration, what are we doing? We're accumulating. So, and then we're going to say the total is $total. This is just a way to format, as you remember, the total into the string. But you all know this formula, probably, right? N times n plus 1 over 2. right? So let's run this. Total is 55, and using the formula, we get also 55. We get a bit of a different answer. We get two different 55s. Why is, so, I mean, okay, most important is to actually understand the logic, right? So if you've never seen something like this, right, or hardly, right, for some people that have programmed a bit, this is straightforward, okay? You've got total, you're accumulating, okay? If you're not, if you haven't, then you need to be in the mindset of, okay, first, you actually run this in your head. You said first line, okay, computer writes total equals 0. Second line, right, max val equals 10. Then it goes, I is going to run 1 to max val. What's max val? Read, oh, max val is 10. Okay, it does this. Then it's going to do assignment, like we said here. Whatever is in total will have whatever was before plus I, right? So at first is 0 plus, first time you actually write yourself, 0 plus 1, right? And this kind of process, if you program it a bit, you do it kind of a bit quicker in your head, okay? But it's kind of that's a process, okay? Secondary thing, much less important, but we're also entertaining here those that have programmed before, is the 0.0 versus the non-0. Why is that happening?
The division of today at floating point, so 10 that you just floating point.
Perfect. Okay. Yeah, exactly. So in other words, division up promotes or casts or changes, right? So if you do 4 divided by 2, even though the answer is just 2, you get a 2.0. How, if I don't want a 2.0, in Python, it's the same. If I don't want a Python a 2.0, what do? 2 slashes, right? So I do this. This is not what Julia is going to do, okay? The 2 slashes are going to work, but I get something else. I get a fraction. I get a rational number, okay, which it factored, all right? So, you know, in Python, this would be integer division. In Julia, it is a rational type. Okay, so if I do type of 4, 2, it's a rational on in64s. Okay, so what do I do in Julia? How do I do this? What I do is I do 4 slash, and then I'm really kind of feeling happy, slash div. I hit a tab and I get this. Now, I don't know if you can see, this is like 6th grade division sign, right? Slash div 2. Okay, so that is div plus tab. Okay, so that's called integer division. What if I do 5 div 2? Now, of course, I could have just called the div function. I could have done div 4 2. Okay, but what if I do, so that's the same. Okay, but what if I do 5 div 2? What's going to be the answer? The integer division is like, how many 2s fit in 5? 2, because the third 2 doesn't fit. Okay, so you're actually going to have so much of this in the computer algebra systems unit with Paul Verbeek, right? The guy that woke up for the lecture yesterday to say hi. That guy. Okay, yeah, he's very cool. All right, so that's that. So we could in this code, now is this thing, by the way, mathematically always guaranteed to be even? You're not just programmers, you're mathematicians, right? It's guaranteed to be even. Why? Because either max val or max val plus 1, either one of them is even, and an even times another number is even, and you can show that. So we could have done here div 2, and then we'd get really the same thing. Okay, a subtle small thing. Okay, not so critical. All right, so that's that. And how do you think, what could we have done syntactically with this line to make it a bit nicer? Some of you would know maybe. Plus equals, right? So thanks. So could have done total plus equal total, sorry, plus equals I. And this is exactly like the commented line above. It's just shorthand. Okay, and in fact, one of the first things Julia does, Julia is compiled. Okay, Python is interpreted, Julia is compiled. Every time you run this, the Julia compiles, and that's why it's fast. It has a bit more latency. So it used to be it used to be horrible. So I first time used Julia in teaching 2017 here to a course called Stat 2201. You do a plot, then you walk around, tell some jokes, etc. You come back and then the plot appears. And then you have to convince the students that it's fast. It's fast, but it had a lot of latency because it compiles, it brings it down to machine language, okay, when it runs. So one of the first thing Julia does is with a line like this, it converts it to a line like this, okay? But this is kind of nicer to look at. Now, you know, plus plus in a language like C++, you could have done x equals 10 and then x plus plus. This is like the most common operator, C plus plus and C, right? The plus plus probably came from this. This is equivalent to doing x plus equals 1, incrementing by 1, okay? But this thing, by the way, I'm toggling comment with command slash, control slash is a common important thing to do, right? This is not going to work in Julia, okay? It doesn't do a plus plus. Okay. This, of course, is okay. All right. And the value of x is while loops. So just before we get into while loops, those of you that have seen for loops and while loops, what's more versatile? Like if you were woken up at night and said, hey, you have to make a choice, for loop or while loop, what do you want to move life with? What do you choose? While? Anybody going with for? Okay, you're all going with while. Okay, you all live. Yeah, okay. Because you see, for loop is kind of like finite, right? You run for on a set. While maybe we don't know, right? You know, you're like, you know, the input continues to go until something happens and then you stop. So the way while loop works is like this. Here's a variable, I equals 1. This is like an if. This is like an if. If I is less than or equal than 3, then you may proceed, right? If this was not true, then don't proceed, right? So for example, if I do, let's go to the REPL a second. Okay, let's open another REPL. And let's do while false exit end. Are we going to leave? Is exit going to be called? No, because it's like an if that false was not true. Now, if I'll do while yikes, I am stuck. Have you ever had a computer program stop working on you? Of course you did. You know, an app hangs, something hangs. You know, sometimes it'd be connectivity or stuff like that. But you know, sometimes what happens is a programmer did something. Well, they didn't exactly know that this is what they're doing, but this is what they've done, right? So, oh my God. So that's it. All right. So std out is now it's true. It's running forever. Let's hope that it has some management and, you know, the memory won't run out or something like that. Control C. Ooh, stops. Julia sometimes doesn't work so well with Control C, by the way. Okay. The reason is it's so fast. It compiles things down to computer language. So the Control C needs like an interrupt to tell it to stop. Sometimes it's so much in its thing and you need to kind of hit it a few times. Okay. Whereas an interpreted language like Python would be much more responsive. Okay. Often when you run stuff in Python, if you've run stuff in Python, you've run like another library, then that library is actually in C++. So Control C is still going to kind of, you have to kind of stop that executing. Okay, so this was the outskirts of the while loop, right? So while I is not equal 3, again, please ignore the fact that we're saying that I is a global variable. Let's println the variable and let's increment it. Okay, so the reason that you chose at night to have a while loop and not a for loop is you saw that the same functionality that you had with a for loop, for I in 1, 2, 3, you could do with just a bit more effort of doing I equals I plus 1, right? But you even know how to do I plus equals 1, so it'll be a bit less effort. Okay, so that's a while loop. So this is this nice example I like, and it's, well, not just me. I mean, the Collat's conjecture. Has anybody heard of the Collat's conjecture? Yeah. Okay. Oh yeah, many. Okay. So does anybody want to kind of state it? if you want. If not, no. No, it's a difference between hearing and being able to say it. It's all fine. By the way, it's not like a heavy conjecture, and I'm not much of kind of a heavy mathematician, right? But this is so nice. It's because you can explain it to school kids. So basically, start with any whole positive number. If it's even, divided by 2, half it. You're going to stay even, right? Sorry, it's going to be divided. You know, one knows says stay even, but it'll be divisible by 2. Okay, if it's even, divided by 2. If it's odd, according to the code, what do? Multiply by 3 and add 1. Is this a syntax error? No, Julia tries to get a bit more popular. And if we have x equals 20, and you could do 3x, and that's 60. Okay. So if y equals 3, could we do yx and this would also be 60? No. So the joy ends here because we don't have a yx. Okay. Oh, 6:55, 5 minutes, 5 minutes. Okay. Sorry, we always utilize the whole hour here, at least that's the thing. But if somebody has a bus, then, you know, priority. All right. So the Collat's conjecture is that no matter where you start with this sequence, you'll end up in 1. And after 1, of course, you'll go to 4, and after 4, you'll go to 2. So you'll end up in this finite sum called 1, 2, 1, 2, 1. Okay. So this is not something we could do with the for loop. So we say we start with some number we want to start with, n equals 7. While n is not 1, then let's first of all print the n. If a condition, what's this condition? What's this condition? Right, it's even, because what do you call the thing on the left-hand side? Modulo, right? So n, so if you do 20 modulo 6, it's the remainder of division of 20 by 6, which would be 2. Okay, so if you do 20 modulo 2, it's always going to be, for even numbers, it's going to be this. So if you do a number modulo 2 equals 0, you're going to check if that number is that number even. Okay, so then we go, if it's even, then half it. Otherwise, do this transformation to it, multiply by 3, add 1, and then you print it. Okay, so just last things before we leave is this is how we define a function. Of course, we'll pick up with that on Monday. And the idea is by the end of Monday, we'll then get to, okay, so I'll have to be a bit faster, but we'll also do some practice questions for the quiz. But then here are like micro projects where you can, these are not for credit, but this is kind of, you know, being able to do this. So some of you that have programmed more, it might be kind of obvious how to glue things. If not, then at least thinking about how to do these kind of with all these basic things. So these are non-mathematical little projects. I didn't know how long will be this kind of unit of 4 hours of speaking and engaging with you. All right. So, but that's kind of the end of this unit. You can do these micro projects, then you get to the real stuff with unit 2 in week 3. So just the last thing before Monday, a function, here is how we define our own function. Okay. What do you use in Python for it? Def. You write def, define a function. Here we said this is a function. That function is my abs, that's its name. It gets an x. And it has 2 things it can do. It says if x is negative, it'll return negative x, otherwise it'll return positive x. So I've now made my own function. And by making your own functions, of course, you can make complex programs because functions interpret. Okay, any last question, thought, something? Thanks for hanging in there. Have a good night. Tutorial tomorrow, 8 a.m. starts the first one, and big homework is out with a video on the website. So good luck. Yeah, so this is tomorrow starting tutorials. Thanks. Thanks.